Hello everyone. This video is about the self-controlled mode or self-synchronous mode of operation of synchronous motor. In this mode, the supply frequency is changed in such a way that the synchronous speed is same as that of the rotor speed. Hence, the rotor runs always in the synchronous speed at all operating conditions. The rotor cannot pull out of the step, hence the hunting oscillations are eliminated in this method. Therefore, the damper windings are not required. Self-control can be realized by making the stator frequency to track the frequency of the induced EMF, which is proportional to the rotor speed. Also, the sensors can be mounted to track the rotor position, called rotor position sensors. The frequency of the signal generated by these sensors is proportional to the rotor speed. The stator frequency can be made to track this frequency. The block diagram shows how to obtain the self-controlled mode in synchronous motor. The rotor positions are sensed by the rotor position sensor or encoder. The pulse change from the position sensor is delayed by an external delay command. In this control, the machine behavior is decided by the torque angle and the voltage or the current. The position signal is given to the control circuit, which will produce the required pulses that can be given to the inverter, which will produce the voltage and the frequency command at which your motor should be run. In this method, the machine can be looked upon as a DC motor without commutator, which has been replaced by the converter. The motor will have DC motor properties both in steady state and in dynamic conditions. Therefore, it is also called as commutatorless motor. When synchronous motor are overexcited, they can supply the reactive power required for the commutation of the thyristors. In such case, the inverter works similar to the load commutated inverter. The natural commutation is possible only when the speeds are above the 10% of the base speed, because at very low speeds, the induced voltages are insufficient to provide the satisfactory commutation. Now let us see the self-control mode by employing the load commutated inverter. So in this circuit, we have two converters. One is the source side converter, the other one is the load side converter. Let us take alpha S be the firing angle of source side converter and alpha L be the firing angle for load side converter. These two converters can be operated either in the rectification mode or in the inversion mode, depending upon the flow of power. When the motor is running in the motoring mode, the source side converter will act like a rectifier and the load side converter will act like an inverter. In case if the motor is operated in the braking mode or generating mode, the load side converter will act like a rectifier and the source side converter will act like an inverter. In large power drives, the wound-free synchronous motor is used, and for medium power drive applications, permanent magnet synchronous motors are used. The source side converter acts like a rectifier for the firing angle between 0 to 90 degree and as inverter for the firing angle alpha S between 90 degree to 180 degree. The magnitude of the torque depends on VDS minus VDL, where VDS is the output of the source side converter and VDL is the output of the load side converter. The power flow is from source side to motor side for alpha S less than 90 degree and alpha L greater than 90 degree. That is when the source side converter is acting as rectifier and the load side converter is acting as inverter. And the power flow is from motor side to the source side for alpha S greater than 90 degree and alpha L less than 90 degree. When working as an inverter, alpha L of the load side converter should be less than 180 degree. in order to take care of the commutation overlap. The commutation lead angle beta L is given by 180 minus alpha L. Beta L should be lesser for power factor of the motor to be higher. The commutation overlap U, it is dependent on the subtransient inductance of the motor. In simple control, the drive of the synchronous motor is operated with constant beta L, which is denoted as beta LC. When good power factor is required to reduce the converter rating, the converter should be operated with a constant margin angle. Gamma minimum is the minimum angle for which the devices should be reverse biased. This gamma minimum should be greater than omega TQ in order to have the proper commutation. We can obtain gamma, which is equal to beta L minus U, where U is the commutation overlap. For successful commutation, as I told, gamma should be greater than omega TQ. Hence, we have to choose the minimum value for gamma in order to have the minimum value for beta L. This gamma minimum should be greater than omega TQ. Hence, we can take beta LC, which is the minimum value and the constant value at which the load commutated inverter to be operated. In order to have the higher power factor, we can take beta L value is equal to gamma minimum plus U. This type of control, where gamma minimum is used in order to obtain the fixed value of beta L, is called the constant margin angle control. A closed loop scheme is shown in the figure, which employs outer speed loop and inner current loop. The terminal voltage is measured by using a sensor, and it generates the reference pulses of same frequency as the machine-induced voltages. A phase delay circuit shifts the reference pulses to obtain the control at the constant lead angle, that is beta LC. Depending on the sign of speed error, beta LC is said to provide motoring or braking operation. The speed controller and the current limiter provide a reference current, DC link current, reference DC link current, ID star, which is compared with the actual DC link current to produce the firing angle for the source side converter. Thank you.